Okay, then let me revise the lecture. John's lemma we basically discussed, that is whenever we have a non-empty partially ordered set in which we have a chain which has an upper bound, then the partially ordered set has a maximal element. So using this result, we proved proposition in terms of L and S, where L is the linearly independent set, which is a subset of a spanning set S. And we found a basis in between L and S. So one application we have seen of this proposition, that is every vector space has a basis. Every non-zero vector space has a basis. So whenever we have a vector space in which we have a non-zero vector, we can always extend it to a basis of x. And on the other hand, if we have a subspace, we have the basis of the subspace, then that basis also we can extend to the basis of the vector space x. So we have seen proofs of this result also. And then we are discussing one result in terms of basis of a vector space. So if we have a linear transformation, so Manvi, what is the, if we have a linear transformation from R2 to R2, so we know this has basis E1, E2, this also has basis E1, E2, right? So we can find T of E1, T of E2. And we can write T of E1, E2, which is element of R2, right? When we apply it on the basis element, we get the element in R2. And R2 also has the same basis, standard basis. E1 is 1, 0, E2 is 0, 1. So that means this TE1 also we can write in terms of basis element. So let me call it K11 T1 plus K21 E1 E2, right? And T of E2 also we can write as a linear combination of the basis element. So that constant I am calling T12 E1 plus K22 E2. So Manvi, what is the corresponding matrix of T? Am I audible, Manvi Upadhyay?
Yes, sir. Sir, K11, K12, and then
Yes,
K21, K22.
correct. So this is basically we studied these things in college linear algebra, as well as you must have seen this in the linear algebra course also. So basically what we are saying is we are given a linear transformation from linear finite dimensional linear space x to y, and if you know basis of x and y, then we can represent linear map as a entries, where what are these entries? Basically this is a, we are writing T of E1 as a basis element of the codomain, that is a column, first column. Similarly T of E2 has a coefficient in the second column, right? So the same thing we are discussing here, that we are having two finite dimensional vector spaces x and y. X has a, instead of it is Rn, now we have an n-dimensional vector space, so it has a general basis x1, x2, xn, and the codomain is m dimensional, so that means it has basis y1, y2, ym. Just correct it. This is ym, and so now every x in x we can write as a linear combination of domain basis, that is x1, x2, xn. So this a1, a2, an are elements of the field. They are the coordinates, and then we are defining the coordinate functions. So that coordinate is aj. So in particular, if we write x1 in terms of basis element, then we know that since x1 itself is a basis element, in the linear combination we only get the first element, which is non-zero. All other elements will be zero. The coordinates of all other x and xj will be zero, right? So that helps here. So in particular, if we find jth coordinate of xj, then that is 1, right? And jth coordinate of xi, that is 0. So that is this map we have written in the combined way. It is a delta ij. So using this function f1, f2, fn coordinate function, we can write every vector as a f1x, x1, f2x, x2, so on, fnx, xn. So similarly, so this we have done so far only for the vector space x. Now the same thing we can do for vector space y, in which this fj function we will denote by gi function. So gi of y is yi, and that also gives gi of yj is delta ij, and then this y, every y we can write as a linear combination of the basis with respect to codomain. So that means y also has the linear combination in terms of y1, y2, yn. So now if we are given a matrix, that means here suppose some matrix is given, we can find corresponding linear transformation. So that is the first thing we verified, that we are given x, we are defining y using kij entry. So what we are doing is we are multiplying kij with the coordinates of x. These are the coordinates of x. So we are getting the ith coordinate of y. Whatever we are getting, that is we are taking as the ith coordinate of y, and using that we are defining y. So y is the output of the function, x is the input. So now we define the transformation for every given x. For every given x, we can find corresponding y. So this is a linear function that we can verify easily. Just take 2x and x dash, and we can verify fx plus fx dash is equals to f of x plus x dash. And similarly, scalar multiplication also is satisfied. And in particular, we get ith coordinate of fxj is actually kij. Right? Using this definition, we can verify that the ith coordinate of fxj. What is fxj? Fxj is the element of y, because f is from x to y. So in y we can find ith coordinate, that is exactly this kij. Here. So this f is linear and this happens. So what we have verified here is basically, let us write down in the sentence. So in this case, we say that the given matrix A given matrix M, that is Kij, that defines the linear map is f with respect to the basis x1, x2, xn of x and y1, y2, yn of y. So we are given basis and matrix, we can find a linear transformation. So now the converse of this. Converse means what? We are given a linear transformation and basis, we need to find the corresponding matrix. So conversely, suppose we are given a linear map f from x to y, then then what we get using the decomposition of y. So what is the decomposition of element of y? That is this one. Y has basis y1, y2, ym. So that means we can define the coordinate functions such that each y we can write as g1y, y1, g2y, y2, gmy, ym. In particular, if we substitute fxj instead of y, then what we get? We get g1 fx j y1 plus last element is gm fxj ym, right? Just substituting y equals to fxj, we get fxj is equals to first coordinate of fxj times y1 plus and so on, mth coordinate of fxj. So this is basically linear combination of fxj in terms of the basis element y1, y2, ym. Yeah, so this is true for every j belongs to 1, 2 up to n. Because what is xj? Xj is the basis element. x1, x2, xn is the basis element of xn, basis element of the vector space x. So each basis element we can find the corresponding coordinates y1, y2, ym. So that is what we have done here, right? We have found in terms of the basis element of the codomain. Now, using these, we will define a matrix M, which is Kij, where what is Kij? We are defining Kij to be using these coordinates. So that is Gi of, that means ith coordinate of the vector fxj. So that we are defining as Kij. So now we have defined the matrix corresponding to the coordinates of fxj. So only thing we need to do is now we need to relate the linear map with these coordinates, right? Basically with Kij. So for that, again we'll use the decomposition of x. Now x is equals to, we know that first coordinate times x1 plus nth coordinate times xn, right? So if we have x equals to this, we can apply the linear transformation on this. So we get fx is equals to f1x is a number because f1 is a, what is small f1? Small f1 is a functional. This is a functional, it takes values in real or complex number. So each fxj is a fixed number, scalar. So when we apply the linear transformation, scalar comes outside, right? So that means when we apply f on x, f will be applied on x, x1, x2, xn. So if you confuse, I can write it one more step. So that is basically f of f1x x1 so on fnx xn, and then these are the scalars. So that comes outside the linear map. Right, and then we know what is fxj. Fxj is exactly this element, right? And what are these elements? These elements are basically kij. So that means you can write fxj as a summation of aij times yj, right? So let us substitute that. So this is nothing but, if we write in the summation notation, this is summation j1 to n fjx fxj, and that is nothing but j1 to n fxj is summation I1 to n kij yj times fjx. So this fjx I am writing on the other side because it is a number. So both these are numbers, so we can switch them, and yeah, so basically we substitute fxj is this quantity using this equation, this one and this one, and so what did we get here? So we get that our linear transformation is defined in terms of the matrix elements, right? So that means every linear transformation if we are given a linear transformation, we get a matrix, and that linear transformation is related to the matrix in this way. Okay, so both the way this method is true, that is what we verified. Fine. So this is regarding the matrix decomposition of linear transformation in terms of given basis of domain and codomain. Now we want to study some examples of functional. So in particular, suppose we have x is n dimensional and y is k. So that means for every x in the domain, so domain elements, instead of writing x1, x2, xn, I'm writing it as a function of n, right? Like a sequence. So x1, x2, xn are elements of kn. Then we define a map fx as a k1 x1, that is first coordinate, plus k2 x2, and the last coordinate is kn xn, where K1, K2, Kn are some fixed, either real number or complex number, elements of K. So then it is easy that f is a linear function and linear function, because it is taking values in, so basically f is a function from Kn to K, is element of K, element of K. So is it clear that this is a linear function? Vaibhav, is it clear? This is a linear function.
Yes, sir.
Okay. So in that case, because for example, if we take two elements, then just we can check that it preserves addition. So this is a linear function and functional, and on the other hand, every functional is of this form. Also, every functional defined on Kn is of this form. Why is it so? Any idea about that? We define any linear function on Kn, it is of this form for some K1, K2, Kn. So that is true because f is a linear functional. So that means it is a linear map. So if you apply f on x, then what is x? X we can write as a x1 time e1, xn time en, right? This is a standard basis. And then f is a linear map. So linear map means what? It is a x1 times fe1 so on xn times fen, right? And now we can see that it is a linear function. So f is a map from kn to k. So that means each of these numbers are, you can call it k1, k2, kn. So that means this is nothing but k1 x1 plus and so on kn xn. So these things we already studied in linear algebra. The thing is this, we are using this k for the common space, which is k is equals to either a real number or complex number. Otherwise, all these things we already know from the linear algebra. So let us see some example which we have not studied earlier. So first example is that let us consider some vector spaces to define these linear functionals. So if we take x is equals to the set of functions, so I'm calling function as a x. So x is not a variable here. X is a function from close interval 0 to either real number or complex number, and we are defining x1 to be the space set of x belongs to this set capital X, such that x is Riemann integrable. On 0 to 1. Right. Similarly, we are defining y1 to be the elements of the set X, so that X is continuous on close interval 0 to 1. And similarly, we can define y2 to be, let us define x2, that is the elements of x, so that x is differentiable on close interval 0 1. So usually we define differentiability on the open interval, but here we are defining differentiability over the close interval. So at the endpoints we can define it in the extended sense. That means at 0 the right derivative exists, and at 1 the left derivative exists. So now consider the function f1 from x1 to y1 and f2 from x2 to x, defined by, so f1 is defined on the function which we are evaluated at s belongs to 0 to 1 as 0 to s xt dt, and the second function we are defining, that is in terms of the derivative. What is s? S is the element of close interval 0 to 1. So here also we know that integration and differentiation are linear operators, right? So therefore f1 and f2 are linear functions, so linear maps. So is f1 and f2 are linear functionals? So answer is no, because you can see that when we apply f1x, so this is element of, this is a kind of functions, you can call it g. So g of s is this function, right? So what is y1? Y1 is the continuous function. So if you remember the fundamental theorem, first fundamental theorem of calculus, right? So that says that if you define the function in this form, then such a function is in fact uniformly continuous. If xt is integrable, Riemann integrable, right? So since this is Riemann integrable, the integral 0 to x naught of the given function is a 0 to x of the function is a uniformly continuous function. So therefore g is continuous. So g belongs to y1. Okay. So these are not functionals, but if we fix the point s, then this will become a functionals. So for fixed value s naught in close interval 0 to 1, define f1 of x is equals to integral 0 to s naught xt dt for x is in x1, and f2x, which we are defining, is x dash of s naught x2. Then again these functions are linear functions, and they are scalar value. So therefore f1 and f2 are linear functionals defined on infinite dimensional vector spaces x1 and x2. So x1 and x2 are infinite dimensional because what is x1? x1 is a set of all functions. So it is infinite dimensional because it contains linearly independent set 1 t square power so on. That is a linearly independent subset of that. And same way, all those elements belong to this set also. So x and x1 are infinite dimensional vector spaces. X2 is also infinite dimensional. It is a differentiable function. Yeah, that is also infinite dimensional. Okay, so now we want to discuss matrix spaces and some examples of infinite dimensional vector spaces, which is related to functional analysis. So if you recall the definition of length, then X be a non-empty set. A metric on X is a map D from X cross X to R satisfying the following axioms for all X, Y, Z is in X. Yes, so Abhimanyu, what are the axioms of metric?
That d of x comma x is equals to 0,
Yes.
and d of x comma y is always greater than 0 if is not x is not equals to y, and third axiom is triangle inequality.
Yeah. Right. And symmetric also. Okay. So the first axiom is basically length is non-negative and length is 0 if and only if the elements are same, points are same. Second one is length of y with x is equals to length of x with y. So that is known as symmetry. And the third property is triangular inequality, that is the length of x and y is always less than equals to length of x with some other point z plus length of z with y. This is triangle inequality. So whenever we have a set given on which we have a metric, we say the set is a metric space. So and whenever we have a metric space, we have a metric defined on some set, we can also define the same metric on a subset. So every non-empty subset of X is also a metric space with respect to the same matrix D. So now let us recall one inequality that is known as AMGM inequality. So AMGM inequality is a very simple inequality. So that is, if we have two numbers, root x and root y, and if we square this difference of these two, that is always square, the number is always non-negative, right? So that means basically if we square this, we get x plus y minus 2 root xy, which is non-negative, and that is nothing but root xy is less than equals to x plus y by 2. So this is AMGM inequality. So this is arithmetic mean of x and y, and this is geometric mean. So this inequality we apply whenever x and y are non-negative numbers. So then and only then we can take the positive square root. So using this inequality, we want to derive some basic inequalities, Schwarz inequality and Minkowski inequality, which are useful in function analysis. So let A1, A2, AN and B1, B2, BN are non-negative. That means they are greater than equals to 0, they are real numbers. Then we want to show the first inequality, which is summation Aj Bj, j running from 1 to n is less than equals to summation Aj square root of these times square root of summation Bj square. So this inequality you must be remembering, that is called Schwarz inequality for numbers. The second inequality is Minkowski inequality, that is for the addition of numbers. So there are many versions of this inequalities. Here we are discussing for finite sum. This also holds for infinite numbers also, and functions also. It is there, nonlinear space also there is a such version. Square root of this is less than equals to square root of this plus square root of Bj square. So let us try to prove this. So first of all, we call this quantity is, in both the inequality we have right hand side is this number, right? Let us call it alpha and beta. So alpha is the number summation Aj square, j running from 1 to n. Beta is the number summation j1 to n bj square, right? So now the question is that if alpha and beta both 0, right? We want to first prove this inequality. So suppose alpha and beta both are 0. Alpha is 0 or beta is 0. So in this case, what we will get? If alpha is 0, alpha is a sum of the perfect square, right? Summation Aj square. If summation Aj square is 0, then what we get is each Aj is 0, right? So if then either if alpha is 0, we get each aj is 0, or beta is 0, we get each beta j is 0, each bj is 0. So depending on whether alpha is 0 or beta is 0, we are getting each aj is 0 or each bj is 0. And if alpha is 0, each aj is 0, so this term is 0, right? If beta is 0, each bj is 0, again this term is 0. In both of the cases, both side is 0, right? So Squar's inequality holds. So suppose alpha is 0 or beta is 0, then this holds, and moreover the Squar's inequality holds. So this case we have discussed that either of them is 0. Now on the other hand, what we have is none of them is 0. So none of them is 0 means alpha is non-zero and beta is non-zero. So that means we can divide by alpha and beta. So for j is equals to 1 2 up to n, using AMGM inequality, for x is equals to, we are dividing each aj by alpha, making it square. So this is x is a non-negative number, and y we are considering is bj divided by beta square. So since alpha and beta are non-zero, we can divide by alpha and beta, and its square is non-negative. So that means we can apply the Cauchy-Squar's inequality on x and y. So what is the Cauchy-Squar's inequality? That is square root xy is less than equals to half x plus y. So let us substitute this here. So square root of x into y is basically aj by alpha, bj by beta less than equals to half x plus y. So that is aj square by alpha square plus bj square by beta square. Right. So this is what we are getting. Now if we multiply alpha beta on the other side, we get aj bj, which is less than equals to alpha beta by 2 aj square upon alpha square plus bj square upon beta square, and then this is true for all j between 1 and n. That means we can take the summation over j. So both the side, if we take summation, we get alpha beta by 2 is a number. So basically we get summation aj square whole divided by alpha square bj square whole divided by beta square, right? And then what can we say about this summation? So the summation we have fixed. What is that? That is alpha, right? Summation aj square is alpha. So that is alpha by alpha square plus beta by beta square. I think I did some mistake in defining alpha beta. I should take square root of this. Yeah. Okay. Now again, if alpha is 0, that means the square root is 0. So its square is 0. Square is 0 means each aj is 0, right? So this is fine. And yeah, alpha beta is non-zero, then we can divide by that. The only step we are using alpha is square root of aj square is here. So basically we get here alpha square and beta square. So that will make this 1. So alpha beta by 2 plus here we get 1 plus 1 is 2. So this will cancel out. Finally we get alpha beta. So what we proved is summation aj bj is less than equals to alpha beta. So that means summation aj bj is less than equals to alpha. What is alpha? Alpha is square root of summation aj square. And beta is summation bj square. So this is the squares inequality. What we have proved. And next thing which we want to prove is the Minkowski inequality. So Minkowski inequality uses the squares inequality. So second part. To prove second part, we'll use the same thing what we proved here. So using summation aj bj, j running from 1 to n, which is less than equals to alpha beta, we get, so in this Minkowski inequality, we want to find aj plus bj square is less than or equals to alpha plus beta, right? So this we want, and here we want square root of that. Okay, so we are taking without square root. We are first considering this quantity. Later on, we'll take square root. So this quantity is, if we use the x plus y square formula, then that is x square plus y square plus 2x1. So if we use that, we get j running from 1 to n aj square plus 2 aj bj square, right? Now we separate these terms. So we get, separating this term, we get summation j1 to n aj square plus 2 times 1 to n aj bj plus summation bj square. So now this term we got, and that we know that that term is less than or equals to alpha beta. So this is less than or equals to, what is this term? This is alpha square, right? Because alpha is square root of this number plus 2 times alpha beta plus this term is beta square. So finally what we get is this is alpha plus beta square. And now we can take square root both the sides. So finally we get summation 1 to n aj plus bj square, square root of that is less than or equals to summation j is equals to 1 to n aj square, square root of that plus summation bj square, square root of that, right? So this is Minkowski inequality. right? So left hand side square root of that is less than equals to alpha plus beta. So this is alpha, this is beta. Okay, so these inequalities are very useful in, we already use in Rn and Cn, and so this thing is useful to verify that Rn and Cn are vector spaces. Okay, so let us take one example of a metric in the finite dimensional vector space, and then we'll go for the infinite dimensional vector space, infinite dimensional metric space. So if you take n belongs to n and x defined to be kn, so that means n coordinates of real number or complex number, for any element x which is defined as x1, x2, xn, and another element y which is y1, y2, yn, kn define. So there is nothing new in this notation, right? Basically we are writing x1, x2, xn by x1, x2, xn, right? So essentially that is same thing. We are considering it as a function of 1, 2 up to n, right? So coordinates we can write in this way. Basically we are using the kind of definition of sequence. So just a different notation of n numbers. We are defining the distance first function d1 of xy, that is defined to be x1 minus y1 plus last term is xn minus yn. So that means we are taking difference of each coordinate, taking modulus of that and adding them. We are defining second function to be x1, taking the difference of coordinate and squaring them, and then we'll take the square root. Right, so basically this is a Euclidean distance, and the last one is we are taking maximum of these quantities. So maximum of x1 minus y1, xn minus yn. Okay. So is these three functions are metric? So these three functions are defined on Kn. So basically it is very clear that each function is non-negative, right? So what are the properties of metric? Let us go back once again. So first property, it should be non-negative. It is 0 if and only if the vectors are same. D of yx is d of xy, and the third one is triangle inequality. So it is very clear that this is non-negative. If it is 0, then each of this term is 0 because each term is non-negative. So d1 of xy is 0. That means each term is 0. Each term is 0 means If this is 0, then x1 equals to y1. Similarly, xn equals to yn. That means x equals to y. Right? So that property is also satisfied, and we can also easily check that d1 of xy is d1 of yx, because we know that x1 minus y1 modulus is equals to y1 minus x1. Right, so using that, d1 of xy is d1 of yx. So only property we need to check is the third property. Right. So note that d1, d2 and d infinity satisfies properties 1 and 2 trivially. So you can check later on why it satisfies, and the only property we need to check is the third property. So to check the third property, we observe that to prove the triangular inequality for the nth dimensional space Kn, we can use the triangular inequality of real numbers. So triangular inequality of real numbers gives xj minus yj is less than or equals to xj minus zj plus zj minus yj for every j is between 1 to n. Right, so this is, we are using the each coordinate satisfies the triangular inequality. So now if we want to show that the third matrix, that is d infinity, which is maximum of these numbers, which is satisfying triangular inequality, then we can see that xj minus yj is less than or equals to maximum of xj minus zj plus maximum of zj minus yj. Right, this is true for every j. So that means this number is less than or equals to maximum of all such number, maximum over each coordinate. Similarly, this single coordinate is less than or equals to maximum over all the coordinates. So now this right hand side is fixed, that is the number d infinity xy xz plus d infinity zy, right? Since we have taken maximum over each coordinate, now this number does not depend on coordinate. Right, so this is true for every j between 1 and n. So this number, which depends on coordinate, is bounded by fixed number, which is sum of these two numbers. So now we can take maximum over the left side. That is less than or equals to d infinity xz d infinity zy, and this maximum is basically d infinity xy.
Excuse me, sir. Please, can you please re-explain this triangle inequality one, that one part?
Yes, so where you have doubt exactly?
What we have taken in this at the start, just that thing only.
So we are basically proving that So we use triangle inequality for k. So what is xj yj? Xj yj are the coordinates of x and y, right? The jth coordinate. So each coordinate belongs to k, right? So each coordinate belongs to k. That means if we take its difference and take the modulus, then that modulus is less than equals to xj minus zj, zj minus yj. So I'm taking other third vector here, right? Third vector is, because triangle inequality we need three elements. So z is just a minute. Z is z1, z2, zn in kn. So we are taking now three elements to prove the triangle inequality. So if we fix some coordinate j, xj, then modulus of xj minus yj is less than equals to xj minus zj plus zj minus yj, because xj yj zj are either real number or complex number. So for the real and complex numbers we have triangular inequality. So each coordinate satisfies triangular inequality, and then we know that if we have single coordinate non-negative number, and that j non-negative number, if we take maximum, then maximum is bigger than each of the number, right? So therefore this is less than equals to this. Similarly, maximum of all such number by changing j is less than equals to this number. So yj minus zj, each yj minus zj modulus is less than equals to maximum of all such numbers modulus zj minus yj. So what is this quantity? This quantity is basically distance of d infinity of x z, and this is d infinity of yz by the definition of d infinity. But this side j is fixed, right? We change j on the only right side. Yeah. So yeah, so basically what we are doing is that if we have a number a1 is less than equals to b1, and b2, then we know that a1 is less than equals to maximum of b1, b2. Right, and if this is true for every I, then this is also true for every I, and then we can take maximum over each ai. So that is less than equals to this number. So that is what we are using here essentially. So now we are taking on the maximum over the left side, and that is the infinity of xy. So the infinity satisfies this triangle inequality for all x, y, z in Kn. So that means d infinity is a metric on the set x equals to Kn. So similarly, we can easily check d1 is also a metric, right? So to check d1 is a metric, so let us call this equation 1 because we are going to use frequently this equation. Okay. So now using equation 1, we get. So what is equation 1? Equation 1 is that triangle inequality in real numbers, and using this we want to prove triangle inequality for real numbers with respect to the first matrix now. So in the first matrix what we have is we need to add all these coordinates. So if we take summation on the both sides, what we get is summation j is equals to 1 to n xj minus yj is less than or equals to summation xj minus zj plus zj minus yj. Right? Just adding this inequality for every j. So basically we get this, and then this is essentially the distance, first distance, d1 of x with y, that is d1 of x with z, and d1 of z with y. This is true for all. X equals to x1 xn, y is equals to y1 yn, z equals to z1 zn. Okay, and so for d1 it is very easy. D1 is a metric. When the set is Kn. So last example is D2 metric. So why D2 is a metric? Because for the D2 metric, let us we consider the notation. So Aj is the notation for modulus of xj minus zj, right? The first term on the right hand side, and bj is the second term on the right hand side, that is right hand side of equation 1, that is zj minus yj. So we are going to use this notation. So let us start with the left hand side. So this is the first page is rough work. Let us start with the next page. So when we take d2 function, d2 of x with y, we want to show it is less than or equals to d2 xz plus d2 yz. What is this distance formula? Distance formula is this is the Euclidean distance. So it is xj minus yj square root of this. So now this quantity is less than or equals to summation. So this term we know that from the equation number 1. Xj minus yj is less than or equals to this number. So if we take square on the both the sides, then we get square of this number is less than or equals to square of this number. So let us use it here. So therefore we get square of this number is less than or equals to square of xj minus zj plus zj minus yj, square of these and then square root of this. Okay, and then we know that in our new notation, what we define here, aj and bj. So this is aj, this is bj, because we are going to apply some inequality in terms of aj bj. So this is square root of summation j1 to n. So this is aj, this term is bj square. So now for this term we have the inequality. So we are going to use the Minkowski inequality, that is this one. So summation aj plus bj square root of whole term, that is less than equals to this term alpha plus beta. So this thing is less than or equals to square root of summation aj square plus summation bj square, right? This is because of the Minkowski. And now we can substitute aj again. aj is basically xj minus zj square plus zj minus yj square. Okay, so this is basically the distances between Euclidean distance between x and z plus z and y. So therefore, and this is true for all x, y, z in An. So therefore, the triangular inequality holds for x, y, z in Kn. Okay. So far we are discussing these inequalities for the Kn. Kn has n coordinates, that is a n-dimensional vector space over K. So we are discussing it is a matrix space when the coordinates are finitely many. But in the second example, we will discuss certain vector spaces which has infinitely many coordinates. So let x be the sequence basically, right? x1, x2, xn, and the first set which we will denote by L1. So L1 is basically, we are going to consider this matrix, corresponding matrix. So we define three matrices, 1, 2 and infinity. Correspondingly, there are three sets. So L1 is such a sequence X, such that each coordinate of the sequence is from K, right? Why K? Because what is K? K is either set of real numbers or the complex number. That means we are going to consider only the sequences with real entries or complex entries. For each J, and not only all the sequence, but the sequence which satisfies this condition. So for the first set, the sequence must satisfy modulus of summation xj is convergent, is finite. So what are these sequences? These sequences are basically absolutely convergent series. So the sequence x1, x2, xn, such that the corresponding series is absolutely convergent. So that is L1. L2, in L2 we are going to take the sequences with either real or complex numbers, so that instead of modulus xj is convergent, its square is convergent, right? So here we have taken only modulus xj, here we are taking modulus xj square. And the final one is all the sequences, so that each coordinate is from k, and instead of in L infinity what we have taken the maximum of the coordinates, right? But instead of maximum, now we have infinitely many coordinates, so we will take the supremum. So supremum of the modulus of the coordinates is finite. So basically supremum exists. So let me give you one exercise. Verify that L1, L2 and L infinity are vector spaces with respect to coordinate wise addition and scalar product, coordinate wise scalar product. So you can see all this verification, you can see it is given in all the function analysis books. So you can open book and try to read this. I will also discuss this in the next lecture. Okay, so let me stop the recording.